Hello and welcome to my channel. Now in today's video we are going to cover formal definition of fluid, strain rate, hydrostatic condition, viscoelastic materials. I will start with formal definition of fluid, and for that we need this background. Suppose we have a solid rectangular block fixed at the bottom and tangential forces applied on its top surface. So that force will tend to change its shape from this rectangular face to this dashed parallelogram shape, and this change in shape is quantified by this angle. We call it shear strain, and this tangential force per unit area is called shear stress. Now if this shear stress is constant, it will develop this constant shear strain, means constant, it will develop constant shear strain, and the constant shear stress divided by constant shear strain is also constant, and we call it modulus of rigidity. So higher value of rigidity means more resistance, it will resist any change in shape, and lower value of G means it will have larger value of this shear strain, means less resistance. But the situation in fluids is different. Now if I take a mass of fluid, say liquid, and I leave it in space where there is no gravity. Now in the absence of gravity, when I leave this liquid mass, it will form a perfect spherical, say, droplet. It will form a perfect spherical droplet, and we know there will be pressure difference across because of the surface tension, because liquids have strong intermolecular force of cohesion, and the pressure inside minus pressure outside will be 2 sigma by r, where r is the radius and sigma is the surface tension. But what happens if I leave this mass of liquid inside the gravitational field? This is gravitational field, means if I leave it on the earth, here on the earth, anywhere on the surface of the earth, or even above the surface of the earth, up to the point where there is a significant effect of the gravitational field, if I leave it, what will happen is it will flow, means that flow is basically change in shape, and not just change in shape, continuous change in shape. This is how we see flow in science. So flow is basically some quantity of matter is continuously changing its shape. That is what we call flow. Now whenever something changes continuously, we say it changes with the time. We give it parameter of time because it changes continuously, and we know time is something that changes continuously, that is moving continuously. So here shear strain is a fixed constant value. Here shear strain depends on time. Shear strain depends on time. That's why in case of fluids we do not use the term constant shear strain, we use the term strain rate. Strain rate. So this is the difference between the solids and fluids. This is where the formal definition of fluids come in, that solids change shape, solids deform by some fixed amount, whereas fluids deform continuously with the time. So we use here constant shear strain, and we use here strain rate because strain continuously changes with time. Now we have hydrostatic condition. What is hydrostatic condition? Now we know that whether it is liquid or whether it is gas, if it is inside the gravitational field, it will always have shear stress, and fluids continuously change their shape even if the shear stress present is very, very small. if it is very, very small. So if shear stress is even very, very small amount, they will continuously change their shape, means they will keep flowing, even if small, very, very small shear stress is present. Since we know we are in the gravitational field, and whether we have some quantity of liquid or we have some quantity of gas, and when we leave it, it will flow. Whether it is gas, it will keep on flowing. Whether it is liquid in hand, it will flow, because there is gravitational field which due to which shear stress is present, and shear stress is present, shape will change continuously, and we have flow continuously. Now, is there any way to make this shear strain go away, to remove this shear strain at all, even in the gravitational field? Yes. How? Suppose in case of liquids, we need a container that is, say, even open on one side, but there should be wall, there should be base. Now, in case of liquids, this is how we remove shear stress completely. When shear stress is completely removed, we do not get change in shape. We have static liquid. And this condition, when there is no shear stress, so this condition where we made shear stress to vanish, or we made shear stress zero, is called hydrostatic condition. Now, we do not need to cover this top surface as well. We can keep it open and still have shear stress zero, or zero shear stress, or liquid at rest. Why? Because liquids have strong force of cohesion, and because of that they have definite volume. Their volume is fixed, constant. Suppose this liquid has 0.5 liter volume, definite volume. Now this container has fixed length, it will have fixed breadth. Now since volume is constant, it will be filled up to some fixed height. And suppose if it is filled up to this height, and even if it is open, it will not come out, because it has fixed volume, height will be fixed, and we can keep one side open. But this is not the case in case of gases. If we have to make shear stress zero or go away in case of gases, so that we can have hydrostatic condition in case of gases, we have to have closed container. We have to have closed container. This is how we can remove shear stress in case of gas, and therefore remove any chance of change in shape, that is restrict to the gas so that it doesn't flow. So in case of gases, having a closed container is how we make this hydrostatic condition. So hydrostatic condition in short means the fluids are at rest, there are no shear stresses, so there is no change in shape, there is no flow. Now since liquids are definite volume, and in a container they will form this free surface under the action of gravity, and the flows which have free surfaces, because they are inside the gravitational, they are suppose inside the gravitational field, they have gravitational effects, they will always form free surface. This is in case of, especially in case of liquids. So liquids which have free surfaces, or liquid flows which have free surfaces, they are dominated by gravitational effects. They are dominated by gravitational forces, and we call them open channel flows or free surface flows. So whenever there is a fluid flow inside a channel, or liquid is flowing inside a pipe but is partially filled, I talked about this open channel flow in the last video. I will put a link somewhere in here. So whenever we have an open channel flow, or we have a pipe inside, liquid is flowing but partially filled with, it will have surface. And open channels like rivers, they have free surface. These open channel flows or free surface flows are dominated by gravitational fields. But this is not the case in case of gas flows. We won't hear about free surface flows in gases, because there is no concept, there is no gravitational effects in gaseous flows except when we study buoyancy. because there are no free surfaces, because no free surfaces are formed in case of gases. When a gas is filled in a closed container, it completely fills the container. If the container is very, very large, it will expand, the gas will expand until it completely fills that large container. Now this is hydrostatic condition. Now if we talk about Mohr's circle, we know in case of solids, if we take a small element here and there is this compressive stress, if there is compressive stress on this top face, there is compressive stress on this bottom face, there is no shear stress on top bottom. But if we cut a section like this, say at an angle theta, at this section which is at an angle theta, there will be normal stress, say sigma dash, and there will be tangential stress tau dash, because this force at that section we can resolve in normal and this. And if we draw Mohr's circle like this is sigma and this is tau, so we have some Mohr's circle, some kind of Mohr's circle like this, and this angle will be this theta, and we know this is twice theta, and we get this point where we have sigma dash value here and we have tau dash value here. But if we have hydrostatic condition, what happens to the Mohr's circle? Now hydrostatic condition means liquid and gas are at rest, no shear stress. When there is no shear stress, that means there is no this part. If there is no this part height, that means this circle reduces to a point. So Mohr's circle will be more like a point, not a circle. So for solids, there is always a shear stress present at any inclined section. There will always be present. So we have Mohr's circle. When liquids and gases are flowing, there will be shear stress present, and we have Mohr's circle. But when we have hydrostatic condition, means liquids and gases do not flow, they are at rest, they are static, hydrostatic condition, the Mohr's circle becomes just a point, reduces to a point. Now next point is this viscoelastic materials. What are viscoelastic materials? Now in engineering, what we study is basically we study substances that are purely liquids or that are purely gases or that are purely solids, like water, like metals, like air. But we have some materials that lie between these materials. For example, what we say solids are elastic, and we refer solids as being elastic, and fluids, we refer fluids as being viscous. We know that they're viscous, and we know in case of solids we have this relationship, and in case of fluids what we have is we have shear stress and strain rate, that is d theta by dt, that is the strain rate. Now in case of solids we have constant shear stress, constant shear strain, and we have this relationship. And in case of fluids we have some shear stress, however small, doesn't matter, and we have strain rate, and this strain rate depends on a property called viscosity. That's why we say solids are elastic and fluids are viscous. But there are some substances which behave in between them. We call them viscoelastic materials. Viscoelastic materials means at one condition they behave like solids, that is they behave like elastic materials, and at other situations they behave like liquids, fluids, that means they behave like viscous. So we call them viscoelastic materials. For example, lead. Lead is solid, it is elastic material, but if we leave it for a very longer time, what will happen? We'll see it has changed its shape, that is, it has gone under some flow like fluid. And same happens with asphalt. So these materials lie in the borderline between solids and liquids. We call them viscoelastic materials. For example, we have a biological fluid called synovial fluid in our knee joint. Now, in knee joint, it acts as a lubricant because there is constant relative motion between these bones. Heat would be generated that will be bad for us. So there is synovial fluid which acts as a lubricant. So fluid property. But this fluid also absorbs shock. While we walk, while we run, it also absorbs shock like solids absorb shock. So this synovial fluid is basically a viscoelastic material. Then there is like ketchup. If we see ketchup or toothpaste, if we apply small push on the toothpaste, it will resist to come out of the paste, behaving like solids. But when we have applied enough force on this, now once it starts flowing, it continuously flows and behave like fluid. So there are substances and materials that are viscoelastic, that have properties between solids and fluids, and those substances are studied in a separate branch we called rheology. Then there are different types of these materials that are studied in rheology, and I will introduce you to these materials a little bit in the upcoming videos. So in today's video, we covered the formal definition of fluid, which basically differentiated the fluids from solids, in the fact that solids have constant shear strain and fluids have a continuously changing shear strain, which we call strain rate. And then I introduced the hydrostatic condition and then viscoelastic materials. That will be all for today's video. Thank you.